Hello students, welcome to the another video of calculus. Today we will discuss the theorem limit of a sequence is unique. Now the statement of the theorem is if the limit of sequence xn, if the limit of a sequence xn exists, if the limit of a sequence exists, then that limit is unique, then it is unique, That is, we have to prove that if the limit of sequence exists, then that limit is unique, that is limit of a sequence is unique. Now to prove this result, to prove this theorem, we will prove this by contradiction. Here we have given that sequence xn and the limit of a sequence xn is exist. So we will say that suppose there are two limits, and if that two limits are equal, then we say that this limit of a sequence is unique. Now suppose this sequence has two limits L1 and L2, and we will prove that L1 and L2 are equal. Now suppose on contrary, suppose there are two limits of sequence xn, suppose L1 and L2, namely L1 and L2. These are the limits of sequence. Now in the previous video we have seen that if the limit of sequence exists, then by using definition of limit of a sequence we can write mod of xn minus L is less than epsilon for all n greater or equal k, that is for every epsilon positive there exists some k belongs to natural number such that mod of xn minus L is less than epsilon for all n greater or equal k. So by using that definition, our L1 and L2 must satisfy that epsilon delta definition of limit, that is for every epsilon positive there must be some natural number k such that mod of xn minus L, mod of xn minus L1, here again mod of xn minus L2 is less than that epsilon. Now assume that epsilon is equals to 1 by 2 times mod of L1 minus L2. Epsilon is equals to mod of L1 minus L2. On contrary, we have supposed that there are two limits of sequences xn, L1 and L2 such that these limits are different, L1 is not equals to L2. Now we have to prove this statement. Here we are assuming this by contradiction, we are assuming this contrary, so we must get some contradiction. So here we have supposed that L1 and L2 are the two limits of xn such that L1 and L2 are different, but we have to prove that they both are equal, and then we can say that this limit is unique. But here we have supposed L1 and L2 are different. Now we have to prove for some epsilon there must some k such that this definition that we have discussed in the previous video fails. Now here for epsilon is equals to 1 by 2 mod L1 minus L2 greater than 0, we will check that definition is satisfied or not. Now our claim is, in this theorem we have to prove that this limit is unique. Our claim is L1 and L2 are equal. Now here L1 and L2 are two limits of xn. Now this L1 and L2 are two limits of sequence xn, then for given any epsilon positive, for every epsilon greater than 0 there exists a natural number. Suppose for L1 there is k1 and for L2 suppose there is k2, there are two natural numbers such that mod of xn minus L1 is less than epsilon for all n greater than or equals to k1, and also mod of xn minus L2 is less than epsilon for all n greater equal k2. Here L1 and L2 are two limits of sequence xn, therefore L1 and L2 satisfies the epsilon delta epsilon n definition that we have discussed in the previous video. L1 is limit, so mod of xn minus L1 less than epsilon. For every epsilon positive there exists this n, there exists this k1 such that for all n greater than equals to k1 mod of xn minus L1 is less than epsilon. Similarly for L2 we can use this definition. Suppose this is equation number 1, this is equation number 2. Now if we choose the k1 and k2 maximum number between this k1 and k2, then these both inequality is satisfied, because if xn minus L1 is less than epsilon for n greater equal k1, and here again xn minus L2 is less than epsilon for all n greater equal k2, if we choose the n, if we choose suppose k is maximum between these two numbers, then both the equality is satisfied for that k. Now therefore let k is equals to maximum of this k1 and k2. If we choose k is maximum between k1 and k2, then both the equations, then equation 1 and 2 satisfied simultaneously. For k is equals to maximum between k1 and k2, both the inequalities satisfied. Therefore for this n greater than or equals to k, we can apply the triangle inequality on mod L1 minus L2, mod L1 minus L2. If we choose this mod L1 minus L2, which is equals to mod of L1 minus xn plus xn, adding and subtracting xn in this inequality, this is equals to this, because just adding and subtracting this. Now here suppose mod A plus B, which is less equal mod A plus mod B xn minus L2 by using triangle inequality. By using triangle inequality, this triangle inequality we have seen in the first chapter. By using triangle inequality we can write mod L1 minus xn plus this mod xn minus L2, which this is less than or equals to mod xn minus L1, just in the modulus we can rearrange the terms, plus mod of xn minus L2, mod of xn minus L1 less than or mod of xn minus L1 plus mod xn minus L2, but this mod xn minus L1 is less than epsilon and mod xn minus L2 is less than again epsilon, which is strictly less than epsilon plus epsilon. Epsilon plus epsilon is equals to 2 epsilon, but we have assumed that epsilon is equals to 1 by 2 times mod L1 minus L2. So this will gives us this mod epsilon is equals to 1 by 2 times mod L1 minus L2. So just putting the value of that epsilon 1 by 2 times mod L1 minus L2, we get this is equals to mod L1 minus L2. So here we get mod of L1 minus L2 is less than mod L1 minus L2. Therefore we get mod L1 minus L2 is strictly less than mod L1 minus L2. Any number is, this is real number which is strictly less than itself. This is not possible. Any number cannot be strictly less than that, again that number. So this is contradiction, which is contradiction. Hence our L1 must be equals to L2. That is, if we choose any limits of sequence xn, then all the limits are equal. That is, the limit of a sequence is unique. Hence sequence cannot have two limits. Sequence cannot have two limits. That is sequence xn has unique limit. Limit of a sequence is unique. Hence the proof of this theorem. In this theorem we have to prove that limit of a sequence is unique. In the proof we have supposed that, on contrary we have supposed that there are two limits and then both limits are different. If the sequence has limit, then that sequence satisfies the epsilon delta definition, the definition of limit, that is xn minus L1 is less than epsilon. For every epsilon positive, there must be some natural number such that mod of xn minus that limit less than epsilon for all n greater or equal k. Here L1 and L2 are two limits, so L1 and L2 satisfy that definition. Here we have supposed that L1 and L2 are different, but here this is wrong because we are supposing this contrary. So there must be some epsilon for which we cannot find L. So if you choose epsilon is equals to 1 by 2 mod L1 minus L2, then for this epsilon we get mod L1 minus L2 is strictly less than mod L1 minus L2, which is not possible. Hence the every sequence of real numbers has unique limit, hence the proof of this theorem. Now we will see some examples on the definition. So the next example is, use the definition of limit. Use the definition of limits limit of a sequence to show that limit n tends to infinity 1 upon n, sequence 1 upon n is equals to 0. So here we have given that sequence xn is equals to 1 upon n, and we have to prove that limit of this sequence xn is equals to 1 upon n is equals to 0. So here we have given xn is equals to 1 upon n, xn is equals to 1 upon n, and we have to prove that this sequence has limit 0 by using definition of limits. Definition of limit is, if the sequence has limit L, then mod of xn minus L is less than epsilon for all n greater or equal n. That is, to prove the limit of this sequence is equals to 0, we have to prove that for every epsilon positive there exists some k, that is there exists some natural number such that n greater or equal that k. We have to find that k. Here to show that, we have to show that limit of sequence is equals to 0, sequence is 0, that is we have to show that there exists a positive integer k, there exists a positive integer k such that for every epsilon positive there exists this k which satisfy for every epsilon positive k satisfies mod of xn minus here limit is 0 is less than epsilon for all n greater or equal k. That is, we have to find this value of k such that for all n greater or equal k, xn minus 0 is less than epsilon. Here if this n greater than or equals to k, then we can write mod of xn is equals to 1 upon n minus 0 is less than epsilon. We can write this. If our n greater or equal k, we can write this. So mod of 1 upon n minus 0, 1 upon n minus 0 is, we can write this. So here this is less than epsilon, but this 1 upon n minus 0 is equals to 1 upon n, and this 1 upon n we can take less than epsilon. From this we can find the value of n. From this inequality we can find the value of n. As this 1 upon n less than epsilon, we can rearrange this, n is greater than 1 upon epsilon, n is greater than 1 upon epsilon. Just rearranging this, multiplying both side by n and dividing both side by epsilon, we can get n greater than 1 upon epsilon. Now if we can choose here n greater than 1 upon epsilon, we have to find the value number n such that which is greater than or equals to k. Now if we choose the k is equals to 1 upon epsilon, then our inequality is satisfied. Therefore for given epsilon positive, we obtain k is equals to 1 upon n, sorry 1 upon epsilon, k is equals to 1 upon epsilon such that mod of xn minus 0 is less than epsilon. Hence limit of sequence xn is equals to 0. Limit n tends to infinity, 1 upon n is equals to 0. To solve such example, that is by using the definition of limits, if you have to show the limit of sequence is equals to L, then we will just consider this mod, we will just consider this n greater or equal k, and using this definition of limit, that is mod of xn minus that limit less than epsilon, we can find the value of n greater than or equals to some number, and we will consider that number is equals to k itself, and we can write this limit is equals to L, or limit whenever whatever limit given to that given in that problem. Now we will see the next example. Same example, use the definition of limit of sequence. Use the definition of limit of a sequence. Use the definition of limit of a sequence to show that limit n tends to infinity, 3n plus 2 upon n plus 1 is equals to 3. Limit n tends to infinity, 3n plus 2 upon n plus 1 is equals to 3. Now here again we have given xn is equals to this 3n plus 2 upon n plus 1. xn is equals to 3n plus 2 upon n plus 1. Now again we have to find the value of k such that mod of xn minus this 3 less than epsilon, then n greater or equal that k. Now to find the positive integer k, for each epsilon positive which satisfies mod of this xn minus limit is 3 less than epsilon. We have to find the positive integer k such that for each epsilon positive that k satisfies this inequality. Now we will consider that n greater than or equals to this k. Then if n greater or equal k, then this inequality is satisfied, that is xn minus 3. xn minus 3 is equals to, xn is equals to 3n plus 2 upon n plus 1 minus 3. So we can just cross multiply and get 3n plus 2 minus 3n minus this 3 divided by n plus 1 Now 3n minus 3n gets cancelled, there 2 minus 3 is minus 1. So we will get minus 1 upon n plus 1, which is less than mod of this 1 upon n plus 1, minus of mod of minus 1 is again minus 1, and this mod n plus 1 is itself, we can write this mod 1 upon n plus 1, and 1 upon n plus 1 is less than 1 upon n. Mod of 1 upon n plus 1 is less than 1 upon n, because n plus 1 is clearly greater than n. If we add 1 on n, then we get the greater number. So n plus 1 is greater than 1, and if we take the reciprocal, then this equality becomes reverse, that is mod of 1 upon n plus 1 will become less than 1 upon n. So here 1 upon n is greater than this 1 upon n plus 1, that is 1 upon n plus 1 is less than 1 upon n. Now this is less than epsilon, mod of xn minus 3 is less than epsilon. Now here we get this 1 upon n less than epsilon, and if we rearrange this, then we get n is greater than 1 upon epsilon. Now again we choose k is equals to this 1 upon epsilon, then our limit is equals to 3. Now here we have, for given epsilon positive, there exists k is equals to 1 upon epsilon such that mod of xn minus 3 is less than epsilon for all n greater than or equals to this k. This implies limit of our sequence xn is equals to 3, that is the limit n tends to infinity, sequence is 3n plus 2 upon n plus 1 is equals to 3. Hence, the solution of this example.